Good morning, everyone. In the first of two of today's lectures, we will cover first some surprises of the simplex method. And what I mean by that is that we will talk about how the simplex method works in some strange situations, and what are maybe some parameters of the simplex method which influence how it behaves. So what we will cover today is first the impact of heuristics, because what we have seen in previous lectures is that the simplex method is nothing but a clever heuristical approach to solve optimization problems. Then we will talk about some inconvenience that can happen sometimes when solving linear programming problems. We will see that we can obtain actually multiple optimal points which are equally good, but they are situated in different locations. We will cover one nasty thing which is called degeneracy and cycling, which means essentially we will answer the question from the previous lecture whether the simplex method is guaranteed to terminate. And actually we will see that if cycling occurs, we might have problems with termination of the algorithm. So essentially the algorithm might run into an infinite loop, which is not good. We will talk about unbounded optimization problems, how to detect them, and also about so-called infeasible optimization problems. Infeasible problems are such that there is no solution which would satisfy constraints. So these are the 5 points for today's lecture. Okay? So let us start with the first point, which is the impact of heuristics. So this picture we have already seen in previous lecture. Essentially what it says is that the optimal solution of a linear programming problem always lies on a vertex. So this green set here, that's called the feasible set. It's the intersection of all inequality constraints. And then we have an objective function which we try either to minimize or maximize, and we hit an optimal point which is here. And there is actually one naive way of solving a linear programming problem, taking into account that we know that the solution is at the vertex. We simply enumerate all vertices of this feasible set, and then we just evaluate the objective function at each vertex, and we take the solution which has the best value of the objective function. Now the problem with this naive approach is that obtaining the vertices is even more difficult than solving the optimization problem, because solving the optimization problem just means finding one vertex, the vertex where the cost function is the best. And actually finding one vertex is easier than finding all vertices. Okay? So this naive approach, it works, but it is not suitable for practical purposes, because finding all vertices would be extremely difficult. Okay? So we just need to find the optimal vertex, and what we have seen is that the simplex method actually starts from some initial vertex, and then it creates a path in this kind of structure which leads us to the optimal solution. And what we have seen is that we can actually reach this point, say, from this initial solution in two ways. Either we can go in this way or we can go in this way. And the way which we are taking in the simplex method is determined by those heuristical rules that we are choosing. Okay? So to remember ourselves, we are looking at linear programming problems where we maximize linear objective function subject to linear equality constraints, and we can also have inequality constraints, but they must be simple in the sense that all optimization variables must be non-negative. And we know how these equality constraints originate from inequality constraints. We simply convert the inequalities to equalities by adding these slack variables, which must be also non-negative. So that's always step one when solving linear programming problems using the simplex method. First, we need to convert the optimization problem into this standard form. And then step two is actually to write the simplex tableau. Okay? So the simplex tableau consists of as many rows as we have equality constraints, and in each row we simply write down the leading coefficient in front of each optimization variable. And here in the last column we have the right-hand sides of those equality constraints. And this final row here consists of the multipliers from the objective function but with the minus sign. And this entry here, that's the current value of the objective function. So currently the objective function is 0, and we will see why. Okay? So when we want to solve this optimization problem, we need to perform pivoting operations. And in those pivoting operations, we have to identify the pivoting variable, meaning the column, and we also need to identify the pivoting row. And here is where heuristics comes into place. We have to, or in the standard simplex method, we are choosing the pivoting column by looking at which of these values in the final row is most negative one. Okay? So we say that the variable x2 would have the largest influence of the objective function. And then we look at the ratios between the right-hand side and the corresponding leading coefficients in the corresponding column. And we choose as the pivoting row the one which has the smallest positive value of this ratio. Okay? So here the ratio is 11, 27, and here it would be something like 16. Okay? Essentially, we are answering the question, which constraint is most endangered by increasing the value of x2? Because we are maximizing. In the objective function, we have all coefficients which are positive, so increasing the corresponding variable will also improve the value of the objective function. But we have to be careful. We cannot increase arbitrarily because we would be stopped by the constraints, and essentially we are looking at which constraints will be reached first by increasing the value of x2. So that answers the question that here it's actually the first constraint which will be violated. So we immediately see that we have some heuristical, some experience-based rules. Pick the column with the largest value, well, largest in the negative sense here, and pick the row with the smallest positive value of the ratio. That's kind of experience, okay? So people have experienced that this appears to be working well, and that's what we called heuristics. And then actually when we perform those pivoting operations, so here the objective is to have 1 as the leading coefficient here, and all other coefficients would be 0, because then the variable would become basic. So that's what pivoting is about, and we continue pivoting until we have negative entries in the last row. So if there are negative entries, we have to keep pivoting until all entries would be non-negative. So essentially then what happens is that these experience-based rules, they create a path in this graph of vertices of the feasible set. But clearly if we choose different set of rules which we apply when choosing a pivoting variable, so here we are all talking about the choice of the pivoting variable. We are not talking about modifying the procedure of performing the pivot. We are only if we would change the variable which would be the pivoting variable, then we might obtain a different path. And clearly in this very simple example, actually, this alternative path would be more efficient because we would only need to perform 2 pivoting operations instead of 3 as here. However, this is kind of a special case. In general, those rules which we have mentioned, they usually tend to perform better than any other alternative. Okay? But in special cases, you might come up with different rules such that you can find the solution faster. Okay? And you might find these kind of settings in those optimization solvers. They might allow to change, for instance, the rules which choose the pivoting variable, and therefore you can also influence the speed of the optimization algorithm. So that's the first point.